Hello everyone, I'm Giuseppe Maggiore. This is the course Introduction to TypeScript, and today in this lesson we're going to focus on functions and lambdas. Now, first of all, a little bit of motivation. So why do functions and lambdas even exist? So as you progress in your career as a software developer, you might notice that you sometimes write code that is that you have already written in the same program, or perhaps even in other similar programs. When you have code that is almost the same but not quite, what do? You typically factor out the differences in code through a process known as abstraction or parameterization. So basically you define a piece of code with holes that can be filled later whenever this piece of code is instantiated. This idea of a piece of code with sort of holes is known as functions. Now, so let's say that you notice that you're building code in a, let's say, sort of mathematical context, and you very often have to perform the same calculation. Okay, and the calculation looks roughly as follows. So let's say that we have one result, result 1, and that would be, let's start with the x. Okay, so let's say we have x1, and this is 10, and then we have some parameters a, b, and c. So a1, that's 5, b1, that's 3, and c1 would be 0. Okay, and then we simply applied the quadratic formula to x, a, b, and c. So x1 squared times a1, x1 times b1 plus c1. Okay, and we have this, but suppose that we have it twice in our program, or perhaps even more than twice. Perhaps we have it 3 times or 4 times, and not neatly next to each other, but even scattered all over the place. Okay, and perhaps even it might be interesting later on to be able to change this program, so that instead of using the quadratic formula, maybe we use something slightly different. Maybe we use a faster approximation or whatever. Okay, now one might decide that, let me alter the parameters, but one might decide that, it's better to group this logic in order to make, first of all, the program more readable, and second of all, to avoid repetition. Because imagine that later on we want to change this formula to something else, or maybe we just even want to add a little bit of logging. We want to print on the console that we are performing this calculation or whatever. Then having this calculation moved to a single, let's say, central place is going to make it possible to change only the central place, and all the instances of this code invocation will be changed automatically. Without further ado, let's define our function. So, the syntax of a function in TypeScript and JavaScript is pretty straightforward. So, we start with the function keyword, then we give a name to the function. This is very important because we're grouping away a piece of code that is going to be deactivated until we actually turn it on. And how do we turn it on? Yeah, by name. So this is the name of this piece of code. Then there are some parameters. The parameters are going to be between the brackets, just like a mathematical function. So we're going to have x, which is a number, a, which is a number, b, which is a number, and c, which is a number. Then I can specify the return type of the function. So what does the function return? Because a function is allowed, and most functions do, actually return something, a value that we can pick up as sort of a result of having executed its code. Inside the function we have a body. The body makes it possible to run some calculation and then give back a value with the return statement. So here we could do whatever we want, but let's begin by simply invoking the function, simply performing the calculation. There we go. Let's see if we can actually get the suggestions of TypeScript in the IDE, because I've noticed that they... Oh yes, okay, now we get the red worm of annoyance back. That's a very useful hint, okay? So now we have the quadratic function. It has 4 parameters, x, a, b, and c. They are all numbers. The function returns a number, and we return the result of this calculation whenever quadratic is invoked. So now, what we can do is we can simply say that instead of writing this big formula, then here I can call quadratic, pass x1, a1, b1, and c1, and res1 will be assigned to whatever value was returned by the quadratic function, with parameters x1, a1, b1, and c1. Here, well, we can more or less do the same, quadratic of x2, a2, b2, and c2. The parameters x1, a1, b1, c1, and x2, a2, b2, c2 will be injected inside the quadratic function, and here they will get the names x, a, b, and c. Now, first of all, let's see if this program works. Always good to, perform a short check. So does it run? It does. Well, I mean, I'm assuming that the calculations are correct. Okay, let's take a look at what's happening under the hood. Let's run the debugger. The debugger is going to stop here at a selected breakpoint. We can see that we are just on the verge of jumping into the quadratic function. Okay, now you can see here that we have a series of local variables, a1, a3, c1, and also, let me close a couple of things we don't need, and also we have x1 and x2. You notice that x2, a2, b2, and c2 are still undefined because they haven't been given a value yet, but room for them has been allocated. But what you also might notice is that there is no mention whatsoever of the variables defined inside the function itself. So there is no mention of x, a, b, and c. This button here allows us to step into the code of the function. Otherwise, we could also just step over, but no, we really want to see what happens when we step inside the code of the function. And lo and behold, plenty of things have happened. This is a very important hint as to how functions actually work. Okay, so you see here, there's the call stack. The call stack has 2 scopes, one on top of each other. We have the anonymous scope, which is at the base of our stack. And this is our global scope. So you can see that as I clicked on anonymous, the line 9 is highlighted in this sort of greenish color that suggests that this line is currently being executed, but as a matter of fact, we're not really on this line, we're inside this line. And you can see that in yellow, there's the proper highlighting of which line of code is actually being executed right now. And that's line 2, that's inside quadratic. If we click on quadratic, we jump into the scope of the quadratic function as it is being executed right now. Notice that also the variables change. So here, if we go back to the global scope, then you can see a1, a2, etc. But if we go to quadratic, all of a sudden there is a whole new set of variables available. Now, this is interesting. So a function and its parameters, and even local variables, as we will see in a moment, represents a sort of little isolated program that has a clear input, the parameters, a clear output, whatever it is that we return, and as little as possible interference with the rest of the program. This is the embodiment of the principle of abstraction. We want to abstract away from all the details of whichever point of our program invoked our function, so that we can just focus on thinking and reasoning about the function itself and nothing else. So you can see that the scope is clean, only a, b, c, and x, only the things that are relevant in order for the function to do its job and nothing else. Now look what happens if I say, okay, let's take a step, let's continue. Well, oh, there's a new variable, return value, because we're evaluating a return statement, and now a new variable, the return value, has been created in order to store the return value. But we're still inside the function, so now the return value has been assigned. Let's take another step, and oh, now it's interesting. Now the call stack contains only the global scope and does not contain the quadratic function scope anymore. Why? Because when you return, the scope of the function that you returned from isn't needed anymore. The function is returning, so it has calculated its result, and now the result has to just be given back. Then you can see that indeed the result has been given back here and assigned to res1. And it's now time to continue to the evaluation of the next function. Okay, so we initialize these variables. We are again right before another invocation, or if you want, instance of the quadratic function with different parameters. We come in. Now, again, the scope of quadratic has been created, added to the top of the call stack here. Inside the scope of quadratic, there are only x, a, b, and c, only the parameters of the function itself. Now we return a value, and this value is calculated and put here in the scope as a return value. And as we finish executing the return statement, the scope of the quadratic function is cleaned up. The value returned is given back to the caller scope, in our case assigned to the res2 variable, and there we go, and the program can safely terminate. Beautiful, isn't it? Now suppose that we really wanted to make this little function a little bit more readable. Okay, so we have the first term, then we have the second term, and then we have the constant term, whatever. Okay, not really a mathematician, so probably there are better names, better official names for this. So please forgive my ignorance. And then we simply return the sum of these terms. I don't know, let's say that someone has decided, okay, such a big expression isn't really readable, we really want to split it up. Okay, legitimate concern. Let's run the debugger again, and let's see what happens to these new variables we've introduced. Okay, so here we are in the parent scope, in the global scope, and you can see there's still A1, A2, etc. There is no mention, as it should be, of first term, second term, and constant term, because, well, they are not part of this global scope. Let's step inside the function, and now you can see we have A, B, C, and X, and those are already initialized, because as soon as you call the function, what happens is that the function is called, we jump inside the body of the function with a new call stack, with a new scope on top of the call stack, and the parameters of the function assigned to the corresponding values passed to the function as arguments by the caller. So whatever value x1, a1, b1, and c1 are going to be assigned immediately to x, a, b, and c right before the first line in the body of the function is executed. Then you can see that constant term, first term, second term, etc. have already been pre-allocated, because I mean TypeScript knows already these variables are coming, but they are undefined. Okay, no problem. Then let's perform the assignments. And you can see that in the global scope, there is still no mention of any of these variables. So calling a function is a way to allocate some memory and to create a series of variables, of temporary variables, that will be cleaned up right after the function is finished doing whatever it is that it was doing. Okay, now the calculation is performed. We get to exactly the same result as before. We just refactored a little bit, and the return value has been created. Then we returned. The scope has been removed from the top of the call stack. We go back to the global scope, and the return value has been given to res1. Let's take a look at this again. Oh, pardon. Let's do it again. I was a little bit too enthusiastic. Let's jump directly to the next breakpoint. Let's step inside. Now, what's going to happen? Think about this. The values of x2, a2, b2, and c2 are the arguments. Those values will be given immediately to the parameters. x2, its value goes to x, a2 goes to a, b2 goes to b, c2 goes to c. The scope for quadratic is created with not only the parameters x, a, b, and c, but also first term, second term, constant term. The calculation is then executed. The return value is allocated and assigned. And finally, the scope is destroyed right after the return value is bubbled up to the parent. It's assigned to res2 in our case, and the program may successfully terminate. Okay, very nice. Now, something I have glossed over a little bit, and well, I'm just going to state that it's possible, is that, and actually I'm going to quickly show it, is that obviously we can have as complex code inside a function as we want. And as our functions grow in complexity and grow in length and richness, etc., well, two things are possible. The first one is to simply move our functions to separate files in order to make our program a little bit more manageable. And if I'm not mistaken, look here, I'm not going to do it because, well, I mean, who cares for this program? But many IDEs, such as Visual Studio Code, even make it easy and possible to move a function to a new file. So this is quite common because separating in files, well, when the function has a good name, clear parameters, clear input types, and a clear return type, well, you don't really need to constantly look at its body. And the sort of intermediate version of this is that, yeah, in some IDEs it's possible to collapse the body, but yeah, I don't think that's a good idea. I think it's a lot better to just move a function to another file and making sure that its name and type are clear and self-explanatory. Inside the body of a function, we can have whatever code we want. So let's say that we have a function that draws a square. And this returns a string. What we do want to know is the size. And then here, well, we have seen this already, but well, let's do it again. Always good, a little refresher. So we're going to build up a square of asterisks. So we declare a temporary variable figure. Nice because, well, draw square. Imperative. Okay, so the fact that we have a figure variable doesn't really matter to the caller. This is just internal stuff to the function itself. So it is nice that we can declare this variable, but no one else but the body of our little function is going to be bothered by it. Okay, then we start by iterating the rows. So for each row called y, then for each column called x, and now we can assign the next, let's say, pixel. There you go, this will be an asterisk. And after having filled up a full row of asterisks, well, we can simply call our figure with add a /n, a new line character to our figure. Now we could have a tiny square, which is a draw square of, let's say, 3. Then we can have a medium square, which is going to be 5. And then we have the large square, which is going to be 7. Okay, now, first of all, as usual, let's run this little program to see. Oops, well, perhaps it's also a good idea to print the squares so that we can also see them in order to inspect the good working of our program. Okay, so we printed the tiny square, medium square, and large square. We run the program, and there you go. Here are our different squares. I'm not going to count the pixels, so you are free to do so from home, but this does indeed look like it's working correctly. Okay, let's inspect the working of this little program. Let's fire up once again our debugger. launch the program. Once again, you can see that in the top scope, in the global scope, we have large square, medium square. Well, we have the function itself, the draw square, because that function is just, in a sense, a variable like any other. And there is no mention of figure, y, x, or size, because those are only meaningful inside the domain of drawing a square. And so the rest of the program is unbothered by them. Okay, now inside draw square, on the other hand, we are unbothered by whatever variables are present in the color domain or scope. So we don't really care about the fact that there's a tiny square, medium square, large square, etc. Here we only have the figure, the size, of course, and that's kind of it. Now, similar to this logic also, inside the for loop, well, now we have the y, and inside this other for loop we have the x, and so on. I'm not going to run this for 9 times, that would be quite boring, but, well, you can see that we have generated our tiny square. Okay, let's also put a breakpoint here. It's always nice to see that the returning is happening. Let's jump inside the draw square of 5. You can see that the size is now 5. We start assembling our figure pixel by pixel. I'm going to jump to the return statement. Okay, so now we have created our figure. Yeah, you can't really properly see it. I hope I haven't botched it. Oh, I ruined it. Oh, that's a pity. By inspecting it, the slash n's have disappeared. Anyway, it doesn't matter. As we execute return, you can see the return value has been created. And then the scope is deleted, but the return value is passed to the medium square. And finally, as we calculate the large square, bam, we get to the return statement. The return statement allocates a return value. The return value is given back. The scope of the draw square is cleaned up, and there we go. The program still works. Okay, very nice. Now, an interesting property of functions is that they may call each other. So, look, let's say that we decide that this piece of code here, that I have just highlighted, as a matter of fact, just makes sense on its own. So, what I'm going to do is, well, I'm actually going to be very lazy, and I'm just going to click this button, extract to function in global scope, that is going to move this piece of code to its own function. This will be draw line. And you can see here that there's a new function, draw line. Okay, I'm slightly unhappy though at the fact that that the thing has decided, the program has decided that the figure, being a variable that was in use, also has to be a parameter. So let me do a little bit of necessary refactoring. Let me just start up a new figure so that when we call draw line, the adding will be done outside. So we keep the boundary of draw line a little bit smaller. So by reducing the number of parameters, I'm actually making draw line easier to use because, well, it is a little bit more independent from the rest of the program. Okay, otherwise, and also, well, also I want to keep the logic of draw square and draw line aligned. So you just give them the size and they give you back the result of drawing that figure in isolation. Also, the version that TypeScript guessed was not bad at all, as a matter of fact. Like, not bad at all. Let's see how this particular program behaves though. Okay, so now declaration of variables inside the scope. So now we have the global scope, the draw square. Inside the draw square scope, we have the figure, we have the size. Inside this block, the block would be the for loop. We have y, very neatly shown, to be completely frank. Okay, now we step inside the draw line. Look what happens. Oh, beautiful. Now we have the global scope, which contains, you know, tiny square, medium square, large square, and also draw square and draw line, because, well, they are also, again, symbols, values, bound to, I think draw line and draw square are even variables, actually, in TypeScript. or constants, whatever. Then on top of this, there's the row square, and the row square, we're stuck on line 12, but you can see that it's this color that says, okay, we are here, but in practice, we're inside this line. We're inside a function in this line, so that's the slightly greenish pale color that says, okay, we're here, but also, yeah, not really. We're inside here. And on top of this, oh, and pardon, sorry, in the row square, you can see there's the figure, there's the size, there's the y variable, and on top of the row square, there is the actual draw line scope with, again, a figure and a size, but there are two figures and sizes, not just one, two figures and sizes. As the function draw line performs its calculation, assigns the return value, and returns it, what happens? Well, you can see that draw line has disappeared now. So the scope of the draw line is gone. And we're back to draw square, and the code of draw square is now marked with a yellow active line marker. Then, eventually, if we let this program run, well, there is another line to be drawn. So there we go, we get stuck again in the breakpoint of draw line. Now, because we ended up in draw line, you can see that on the top of the stack there is draw line with figure and size. Inside draw square there are y, figure and size. Now this is the second row, so y has a value of 1. Take a step. The return value has been allocated inside the draw line. The scope here on top of the stack is about to be cleaned up, and indeed the scope is cleaned up, and we are back to draw square, and so on. We let this program run to completion, and there we go. So we have seen basic functions in order to capture pieces of code that we might want to instantiate with slightly different initial conditions. These initial conditions are specified by the parameters of our function. The name of the function is a very important, for the programmer at least, descriptive bit that specifies, okay, what does the code inside the function do? And finally, the function, when it's done, will return a value. There are also functions that don't return a value, but those are called procedures. And, well, there is some thinking to be done about whether or not it makes sense to have functions that don't return a value, but that's a philosophical discussion I'm not going to get into. And anyway, when the function is done, it can return a value, clean up everything it has done, minus obviously the value which is saved for future reference. Okay. Now that we've seen the basics of functions, let's dive into a very powerful, somewhat advanced, and also somewhat complicated technique that we can apply to functions. Now, as we have seen, every time we call a function, the function stores the parameters and local variables in a separate location in memory. So it doesn't mean if the function has been called from the main program, from another function or whatever, it will work in an isolated manner. This implies that we can call a function from anywhere in our program. Like we see right now on the screen, we call draw square from the main scope, but we also call draw line from inside draw square. But for draw line, where it's being called from, doesn't matter at all. It just knows it has to allocate its space on a stack. It has the size, it has the figure, it has the x variable, it does whatever it's supposed to do, it returns the figure. Now, this means that a function might call itself. And every time the function calls itself, well, the recursive call, so the nested call, will simply have its own independent area on the stack. It will have its own independent logic. It will run this independent logic and return to the caller, which is itself. This is very similar to while loops, but also at the same time more powerful than while loops. Now, let's reformulate the draw line function in recursive terms. Now, recursive terms require a problem to exhibit, let's say, self-similarity. So what is draw line going to do? draw line is going to turn a number, a size, let's say a size of 5, into, well, let me put this thing inside the comment, then the compiler doesn't complain. Okay, so 5 turns into 5 asterisks, 4 turns into 4 asterisks, and so on. And 0 is the degenerate case, the base case. Well, for 0 we just return the empty string. Okay, now you might notice that inside, for example, inside the 5 row, the 5 line, you could say there are multiple smaller lines. So we could consider the draw line of 5 to be equal to, well, any decomposition of this into smaller lines. So you could say that this is the same as a draw line of 4 plus a single asterisk. And the same applies to draw line of 4. We could say the draw line of 4 is the same as draw line of 3 plus a single asterisk. So every time we fall back on the function itself, but because we do so on smaller parameters, eventually we will get to 0. And when we get to 0, we know what to answer. Let's do this now. So if the size is, well, actually I'm going to say smaller or equal than 0, and that's it. I just return the answer because we know it already. Otherwise, we return draw line of size minus 1 plus a single asterisk. Probably we are missing a type annotation, and there you go. Look at this. Like, it might also feel a bit mind-blowing that there is almost no logic anymore in this program. And if you wanted, you could even reduce the size of this code further by using a conditional expression and just returning directly a single result. So if the size is smaller or equal than 0, we return, well, directly the empty string, otherwise the row line of size minus 1 plus asterisk. There you go. 4 lines of code have shrunk down to literally just 1, and it's also quite a trivial line of code. Okay, now you might actually you might notice that draw square is very, very similar. Now, not entirely, because for draw square we have to track both the width, which stays constant, that's the size, and the height, which changes. So you know what? Let me reformulate draw square in terms of draw rectangle. Okay, then we have the height, which is a number, and the width, which is a number. Okay, so how many rows do we build? Well, the height, and every line is going to be of width. Okay, now, so first of all, the square, you might imagine, is just a rectangle where the width and the height have the same size. Okay, but now you can imagine that the draw rectangle, we can apply the same principle as the draw line. Actually, exactly the same principle. We could say that when the height is 0, well, it's a degenerate rectangle, so if the height is smaller or equal than 0, and this way we don't have to think about what happens if someone by mistake asks for a rectangle of height minus 5, for example, because that doesn't make any sense. So we simply say, okay, if you ask something silly, you just get an empty rectangle. Okay, that's it. Okay, so if there's no height, great, then there's nothing to do. Otherwise, well, there's a full row, so draw line of width. The full row has to be terminated by a /n, by a new line, followed by a rectangle with, well, one row less. But the rows are all the same size. Bam, there you go. Again, thanks to recursion, one single line of code. Let's see if we've broken anything. No, we haven't. One of the very weird properties of recursion is that it feels incredibly complicated and surprising when you start your career. I think it took me the best part of 3 or 4 years of intense effort to really understand recursion properly. And then when you know it, It's the simplest and most logical thing ever. So it's kind of that is kind of funny. All right. But when you get it, as you can see, you get code that is incredibly elegant and actually fairly simple to read. All right. Functions, just like anything else, are simply variables. So draw line, as a matter of fact, is not really a special construct. And these variables have as value the value of a so-called lambda expression. So a lambda expression is a function that we simply manipulate like any other value in our program. Let me see what this means in practice. So I could say the draw line is, and then there is a slight difference in syntax between lambda expressions and functions, because then I could say, okay, draw line is the anonymous function, because the function as defined now doesn't have a name anymore. There's only the function keyword and then the parameters right away. And now draw line, well, now it's a constant, but I could even say that if I define it as with a simple let, that is as a variable, then it will be possible to also change the implementation of draw line. The fact that functions can be any regular, like any other regular value, so there is no intrinsic difference between a function, a string, or a number, because they can all be manipulated in the same way. You can have functions inside conditionals, you can pass functions as parameters to other functions, you can return functions from other functions, and so on. So this means that, well, we do have a lot more power at our disposal than you might imagine. This is so important that there even exists a simplified syntax for defining lambda functions that only have parameters and directly a body which only returns an expression. So draw line falls into this category, so we don't even need to have the function keyword. We can put an arrow here, so equal greater than is an arrow. We can remove the curly brackets and return, and we can shrink down the drawLine function to a really minimal size. Unfortunately, TypeScript is not smart enough to guess that this is a string, but that's okay. We can also do the same with rectangle, for example. We can say that draw rectangle, while it takes as input height and width, returns a string, and then the thing it returns doesn't need to be specified so extensively, because we can just put the expression that we want to return right after the arrow, and that's enough. If we really want to push it, but I wouldn't do it. To be honest, also for the draw line. It's easy to underestimate the importance of organizing code like this, but having less lines of code means that there is going to be less scrolling, there is going to be less searching, more code compacted down, boiled down to its most expressive form will be available and right in your face as a developer. And making sure that the most important aspects of your program come to the surface without any boilerplate, without any confusing bits, can be very important. For the rest, this program is exactly the same as the previous one. Now, draw line, draw rectangle, and draw square are, in this case, lambda functions. But this is not exactly the most interesting example of lambda functions. Let me give you a slightly more interesting demonstration of how lambda functions would work. So let's go back to redefining figures in the most generic way possible. I will leave this code here because we might want to play with it again. So draw figure. In general, draw figure will take a width, which is a number, a height, which is a number, return a string, and okay, what do we do? Well, we have the let that builds up all the rows. So for each row, then we have the for that iterates the columns of the current row. So for width, Okay, cool. Then we have to accumulate, of course, the result of drawing the whole figure. We start at empty. Well, here, in the case of, let's say, grayscale, we're going to have either an asterisk or a space. Oh, pardon. Well, we will add either an asterisk or a space, and at the end of the row we have to add a /n. Now TypeScript is complaining, thankfully, well, and let's be thankful for its relentless attention to our code, that we aren't returning anything, but now we are. Okay, and we can draw basically any figure by simply providing a way to pick which one of these two, the asterisk or the space, has to be added for every pixel. So is pixel on x, y, and if the answer is yes, then we add an asterisk, otherwise we add a space. And you know what? I have a feeling we will not need the rest. Okay, but is pixel on? Well, you might imagine that is pixel on will change depending on the figure we want to draw. So we might say that this logic is okay, is very generic, and we add an isPixelOn parameter. What will be the type of isPixelOn? Now it will be a function, and here the type of functions looks a lot like the syntax of the heading of the parameters and the return type of a lambda, because isPixelOn will effectively be a lambda. So we have the x, which will be a number, the y, which will be a number, and we expect to return a boolean. Oh, pardon. And this comes with an arrow. That's a slight inconsistency with respect to other aspects of the syntax, but it actually makes sense, because the domain of functions, in the domain of functions, the type would be that you take two numbers and you go, so the arrow really signifies you go, you compute, you move to a boolean. So, you know, I can live with this, and I hope you can live with this too. Okay, now this thing, I hope you appreciate the fact that this thing looks like it's actually working, you know, so quite impressive. Okay, let's draw a figure. Well, let's say 5 by 5, and isPixelOn will be, well, we take the x and the y and we simply return true. All the pixels are on. Let's run this. There you go. We get our first square, our first filled square. Let's return false. It's empty. Okay. X is 0. Okay. So you see that even though draw figure is clearly quite opinionated as to what logic it's implementing, I mean, it is clearly implementing some logic that is performing something. At the same time, it's also incredibly flexible. Now, this is the result that we achieve with lambdas, and this is the reason why so many modern libraries in the JavaScript and TypeScript world feature lambdas very prominently, in order to provide an algorithm which, on one hand, is complete, but on the other hand, can also be heavily customized in the locations, in the places where this customization really matters. Okay, let's give names to these functions. Okay, so we had the full square, which was, well, let me give a type to this. So we have x number, we have y number, returns a boolean, and this simply gives us, pardon, okay, so this is the type, and this is the body, and the body will be x, y goes into true. There we go. Okay, now, apologies for the moment of confusion, but yeah, it happens when doing live coding. Okay, so here, first I have the type of this variable, and then notice that I don't have to say that x is a number and y is a number, because it's clear from the type. Okay. Now, I don't know if you prefer to have them aligned. Yeah, this might be quite stylish. Okay. Then we have the top row. Now, what is the top row going to be? Ooh, no, this misalignment is terrible. No, 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 no. Okay, perhaps this is better. No, this also looks ugly. Ah, whatever. You know what? I will leave them like this and not care. Okay, so what is the top row? The top row is y0. What is the first column? The first column will be x is 0. Okay, now unfortunately we have a little bit of a problem, because if we wanted to define the last row, in order to define the last row or the last column for that matter, we need to know the width and the height. Okay, no problem. So we just extend our ispixelon function with the width and the height. Now ispixelon gets invoked with also the width and the height, so that we provide a little bit more logic. Interestingly enough, you might notice that the draw figure function is not really complaining about the fact that we're passing it a lambda that takes less parameters. So ignoring parameters in the JavaScript world is always allowed. Huh, okay, so not really useless. Let's see if this holds to the variables, and actually it does hold. Very good. And this is an example of a sort of polymorphism. So we're not really passing something that has exactly the type we need, but by virtue of being close enough, actually by virtue of being a well-behaved subset of what we expect, it's okay. There is no danger. Ignoring a parameter is not really dangerous, so it always works. Okay, so full top row. Let's test everything. That's always a good idea. First column, also always a good idea. Bam, there we go. Now we can define the bottom row. Now for the bottom row, we do need the width and the height, because the bottom row will be y equal to the height minus 1. So that would be the last row. Okay, how about the last column? Okay, for the last column. Why? Of course, because the type of the parameter and the implementation have to define the well, the type and the implementation have to define the parameters twice. Okay, very good. So let's test the bottom row. There we go. Okay, and the last column also working. Yes, very good. Okay, now let's go for mind-blowing. Are you ready? Okay, so what if I wanted to have both the first column and the last column? Okay, oh, I could do it as follows. I could define here lambda that calls, we said the first column. Well, it doesn't matter, any two functions. Okay, so I call first column with x and y, and then I put an OR that says last column x, y, w, and h. Now for completeness, I might think, no, TypeScript is not that cool with this, but alright. I can't really pass extra parameters explicitly. I can only do it implicitly by putting a lambda in an argument. Okay, and now, okay, I have two. Ooh, interesting. Now, let's define a higher order function, so a function that takes as input lambdas and returns a lambda that combines the original two. Let me do something that we are going to explore deeply later being in the next lesson. So let me define a type of ispixelon so that I don't need to repeat this declaration. So here, in this type, I will just give it a name. Now, saves me from repeating a mountain of times this ugly thing. You know, nice, isn't it? All of a sudden our code is getting cleaner. Yeah, that's why I wasn't that afraid. Okay. Oh, I forgot half the declaration. No, it's either all or nothing. Okay. Now also, because first column has been declared as ispixelon, well, it takes the width and the height. Okay, very good. Now, let's define the plus combinator. Plus combinator will take two functions, f, which is an is-pixelon function, and g, which is an is-pixelon function. And they might be, well, top row, first column, bottom row, last column, even full, though full is not very exciting. And what do we get as a result? We get the combination of these two functions. Okay, what is this going to look like? Well, this is-pixelon function that we're building is sort of a synthetic combination of the original two that calls the first one f and the second one, and if either of them says yes, says true, then also their sum also returns true. Look what we can do now. What we can do is we can simply say plus of, well, top row and bottom row. Bam! But because plus is an is-pixelon function, look what we can do. We could even say plus top row and bottom row and add it to the sum of first column and the last column. And there you go. There's the hollow square. Now, let me show you also something else. Now, one might say we could create, let's say, the rectangle triangle, which would be x smaller or equal than y. Now, I will give a name to this thing because it's way too pretty. So const hollow square would be this, and the triangle. There you go. But let's say that this is lower left triangle. Okay, so triangle lower left. Okay, very good. Oh, well, of course the thing is complaining. All right. Now we can also define other variants of plus. So for example, we could call plus by flipping coordinates. So call a similar function to plus that flips the coordinates of the function it's invoking. So flip horizontally. Now, okay, so we take a function is-pixelon and we return a new is-pixelon, again synthetic, that calls, well, not exactly x, y, w, and h, but rather, because we flip horizontally, we call w minus 1 minus x. Now, let's call flip horizontally of the triangle lower left, and there you go. Okay, perhaps we can get away with also flipping vertically. And of course, well, this is going to influence the y. Oh, well, perhaps I should... And there you go, we flipped vertically. And obviously we can flip horizontally and then vertically. And now we're going to get the last rectangle, the last triangle. Okay, so we have the triangle lower left, but let's have the triangle lower right, which is going to be flip horizontally of the triangle lower left. Okay, let me make sure that I'm not confounding myself. Okay, this is triangle lower right, very good. Then the triangle upper left will be flip vertically of the triangle lower left. Again, testing, because this is not exactly intuitive. Okay, upper left, yes, makes perfect sense. And finally, triangle upper right, and this will be the flip vertically of the upper right. No, this will be the flip horizontally of the triangle upper left. And once again, quick test. Okay, but funnily enough, now what's happening, and I hope you can appreciate this, is that we can also use our intuition. And our intuition about yeah, just figures moving around, like pieces of paper moving and being flipped, etc., is very powerful. So now we've taken a domain, the domain of, you know, loops and recursion, etc., which is very difficult to reason about, and thanks to higher order functions, we've made it possible to build the same intuitive combinators that we would use to think about this if we were drawing as children on paper. So this is very powerful. Obviously, it requires a machinery that is not trivial at all, but the result is beautiful and almost feels trivial. And the amount of code is very limited. I mean, it's a very powerful and flexible system in, what, 33 lines of code. But we're not done yet. Okay, so now what we're going to do is we're also going to introduce another combinator, because very much like plus, there is another combinator which is the multiplication, and the multiplication means that we want only the pixels that are on in both pictures. So we want both f and g to return true for that same pixel. Now, so let's say that we have the triangle lower right. Oh, triangle lower right. There we go. Okay. And the other triangle lower left. And let's say that we multiply them. Triangle lower right, triangle lower left. And what we get is a pyramid. Now, that's just a stencil, so we're putting them, so we're using one as a stencil for the other. And let's say that we also want to have a little frame around it, so we could say that we have the hollow square and the pyramid. Well, it's kind of ugly when it's this small, but fix it quickly. Just let me give a name to the pyramid. Let's make it a little bit bigger. When it's bigger, it's clearer what it's doing. Oh yes, okay, now you can see it a little better. Let's say, obviously, odd numbers work better. Yes, so this is a pyramid. This is a pyramid in in a simple. This is a pyramid in a simple frame, and you can imagine that by simply defining a new isPixelon function, you retain all the power of all the isPixelon functions that you have already created before, because you can still combine them, plus whatever new logic, new beautiful logic you've invented. And this is the power of higher order functions and lambda expressions, and it is absolutely unbounded, as we will see in the rest of this course. This concludes the lesson on functions. So, as always, thank you very much for being here. Thank you very much for listening. I hope this course is contributing to spreading the beauty of programming and also helping you appreciate the wonders of this amazing programming language that is TypeScript. I wish you the absolute best of luck with your studies, and until next time.